Matilda, I nailed the ramp balance. Now the crew wants Wi-Fi.
Nice update. Where are you putting the router?
I need a spot nicely in the middle so everyone gets fair signal.
So a point equidistant from the ramp, bench, and shop?
Exactly. Same distance to all three spots.
For same distance, we need the perpendicular bisector. Let's say A and B are two spots. We want a line equidistant from them. Construction is key. This red line is the perpendicular bisector. Perpendicular, 90 degrees, and bisects, cuts in half. And there is only one such line for any segment. If you put the router anywhere on this red line, the signal distance to A and B is identical. Why? Let's prove it with SAS congruence. 1. Side AM equals MB, bisector. 2. Angle 90 degrees at M, perpendicular. 3. Side PM is common to both. So by SAS, the triangles are copies. PA equals PB.
What if I just find a point equidistant to A and B?
Then it must be on this line. Let's prove the converse. Since AM equals MB and PM is perpendicular, PM is the perpendicular bisector.
Solid. If distances are equal, it's on the line. So if the distance to the bench is 14,
Then the distance to the ramp, 3x plus 2, must also be 14. Exactly. X equals 4 solves the equality. Now, let's apply this to a triangle side.
okay, drawing the perpendicular bisector of the bottom side. Whoa, the line missed the top vertex.
Correct. The perpendicular bisector ignores the vertex. It only cares about the midpoint of the side.
Okay, I have 3 spots. How do I find the equal distance point?
Draw PB of the ramp bench side. Any point here is equal to A and B. Draw PB of the bench shop side. Any point here is equal to B and C. They meet at O. Since O is on both lines, OA equals OB and OB equals OC. So OA equals OB equals OC.
What about the third side, ramp and shop?
Ideally, it passes exactly through O. Theorem. The 3 perpendicular bisectors are concurrent.
So O is the center of a circle hitting all 3. Cool. So if the ramp is 10 meters away,
The bench and shop are also 10 meters away.
perfect coverage. Thanks, geometry. So O is always inside the triangle, right?
Is it? Let's check various shapes. The center O stays fixed. Let's move the triangle points. Acute triangle. The center O is inside. Right triangle. Angle A is 90 degrees. A 90-degree angle on a circle opens to a diameter. So the hypotenuse is the diameter. It must pass through O. Crucial property. The midpoint of the hypotenuse is equidistant to all vertices.
So AO equals OB equals OC. Handy trick.
Yes! Can we prove it? Isosceles triangles. OA equals OB and OA equals OC make two isosceles triangles, so base angles match. Sum of all angles is 180.
Divide by 2. Beta plus gamma is 90.
And beta plus gamma is just angle A, so angle A is 90. Obtuse triangle. The center O is left outside. See? The triangle is too small to hold the center. Theorem. If you are on the line, you are equidistant. Converse. If you are equidistant, you must be on the line. And remember, every segment has exactly one such line. The three lines always meet at one point, the circumcenter. This point O is equidistant from all corners. Finally, inside for acute, on edge for right, outside for obtuse. That's how perpendicular bisectors ensure fair distance.
Off to set up the router. Thanks, Matilda.
You're welcome. Don't forget to subscribe to Mathilda Academy.